Whoa, 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 whoa. Yeah. What is going on here? I think the broadcast has just started, right? So since this very moment, Radek, people can see us and hear us. I hope for it, actually, but we have to be very careful what we say from now because we are too lazy to cut the webinar, right?
Yeah.
Since ever, but we do not cut it anymore. So this will be part of the recording already. Yes. So the last check, Radek, is everything working? Do you think it's
Yes,
working?
I hope so. I can see you. I can hear you. So I think
I
from your side, everything is working. I'm not sure
okay.
if you can hear me.
I can hear you. I can see you. Yes,
Great.
yes, yes. And yes, Radek is sitting in our bigger meeting room, right?
hmm hmm
In our CFD support
With a
office in
nice,
Prague.
yeah.
Yes, CFD support. Yes, so bigger meeting room, and I am in exile, right? In exile in the smaller meeting room, right? Which is
Yeah.
not as nice as
Yes.
Radek's room, right?
Please
Right? Not
don't
at,
move your
at all,
camera, right?
not at all. But
Yeah,
yes,
don't move your camera.
I won't. Yes, good point, Radek, good point. It has to be set exactly this way, and people should see only this, what you can see, which is, by the way, quite, in my opinion, Radek, it's quite like sterile environment, right?
Yeah.
It's like white nothing. I'm sitting
Yeah,
in
we
the
should
middle
equip
of
it by
nowhere
some
in the small
nice
meeting
pictures.
room
Okay.
with nothing, right? And you know what? I'm still quite happy because we are having webinar today and we are engineers and our happiness and our I would say entertainment is not on the walls, right? It's in the
Yes,
computer, right? And it's simulations.
exactly.
It's
Yes.
accurate results and converging simulations and happy clients and happy friends and happy everyone. So it's one long parade
Perfect.
we are having here for 15 years already. Yes.
Oh
And
yeah.
by the way, on my clock it's 2 p.m. So let's get to the action. Right. So Radek, the webinar is has to start, but
Yeah.
I
It's
need to
being
share my
recorded.
screen.
Yeah,
I
it's
need
being.
to
I think it's
it's being
recording. Yeah.
recorded. Okay,
Yeah.
and I'm going to share my screen, which is this. I was
hmm
just playing a little bit with my presentation. I will home it, and I think it's time to start the webinar, right, Radek?
Yeah. It's already
Okay.
started.
Okay, it already started, yeah, so people can see this and yeah. So yep. So okay, so I will wait 5 seconds in completely in silence, and then I will start. Hello everyone, this is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar where we will show you how to create perfect CFD simulation setup, right? So as you can remember, the last webinar was about CFD pre-processing. It was about how to prepare simulation ready geometry for simulation setup. And today's webinar is dedicated to simulation setup. So we are looking forward to it. So what else? The webinar is being recorded and its recording will be later made publicly available on our YouTube channel. So yes, there will be a recording, a typical question from our users and attendees. So there will be a Q&A session at the end where you can ask your questions. So feel free to ask your questions. This webinar is quite content-like webinar, so you can see a lot of important information for engineers. It's not one big ad on our products, but it's really I promise you can really learn things in the webinar, and we will be happy to share it with you. Okay, so we have this setup. Together with me online, I hope still is my colleague Radek Máca. Hello, Radek.
Hello, Luboš, and hello to the audience. And I wish you a good day and great webinar today.
Yes. Radek, it's a pleasure to have you here because you're the the real expert here. I'm only responsible for communication with our users and with our partners. So thank you for being here with us. And I think we can start. We can start and let's see what we
Yes,
can do.
yes, but and don't be so humble. You are also expert in CFD, definitely.
Okay, thank you very much. Okay, okay, yeah. So let's do that. Let's do that.
Yep.
I'm doing it. And also, Radek, I think this is the very time we will switch off the cameras
Yep.
and provide our users even better aspect ratio of the on the display. So
Definitely.
yeah, we are still here, but our images are going away for a while. So I'm switching off the camera. So yes. So I hope our users can see pretty much my screen at the moment.
Yes,
Okay,
I
so
can
the
agree.
webinar is really here. This is the agenda. So in the 5 minutes, but yes, only in 5 minutes, I will mention all the necessary information about what's on the table. If I'll be longer than 5 minutes, I will buy you a beer when we will meet personally next time. If I'll be longer than 5 minutes, so I'll be very careful to be shorter than 5 minutes. Then we will start with general thoughts about what we think about how the simulations should be done, could be done. And we'll start with general thoughts, and we will be going to more and more particular details in the webinar. So we will start with general thoughts, what we think of about how to set up simulations, what are the smart tips and tricks, and special how-tos, what we think it should be done. And then we will go more to like goals, principles, and thinking of engineering simulations. And then we have two cases. In the first case, again, it will be rather quite general, very simple pipe flow. I'll show very quickly some principles about how to set up the case. But yeah, very simple. And in the larger case, Radek will show quite a detailed, more detailed example how to set up, specifically how to create the mesh, because it's always very important to create the mesh, and how to set up the critical settings of Kaplan turbine. And then there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions anytime during the webinar. We will answer all your questions. The most relevant and representative questions will be answered right away in the webinar, and the rest will be also answered, but via email when no, tomorrow, I guess. Yes, and there will be then the conclusion, of course. So I will start with when one idea which just popped up in my mind. We will be showing things in our simulation environment called TCAE, but we will show general principles. So you can be sure that if you have another CFD software or standard CFD software, you can find the similar settings, similar principles. There's only one nature and one universe, and typically the simulations are done similar way. So yes, we will show everything in TCAE, but the principles are universal and pretty much useful, I guess, in other software, especially in open source, open form, etc., etc. Okay, so I will start, and I'm starting now those promised 5 minutes on my timer. Yes, so the next webinar will be dedicated to CFD post-processing. So today we will not speak too much about CFD post-processing. Today it's about CFD simulation setup. So once again, I just repeat, this CFD simulation series is about, the last webinar was about pre-processing. Today's webinar is about simulation setup, and the next webinar on June 17th will be about CFD post processing. So today it's about the mesh and simulation setup. Okay, so looking forward to it. Just quickly, CFD Support is the company name. We are located in Prague, Czech Republic, 15 years in the market, hundreds of professional projects, consultancy projects for the industrial users of and industrial applications, and much more to come. We deal with CFD, FEA, FSI, optimization, and acoustics. So we primarily deal with engineering simulations. We are quite compact, small team of well-educated engineers who take the things very seriously. We provide consultancy business, of course, and consultancy projects, and also we develop software which is comprehensive simulation environment called TCAE, which is software which includes several software modules. These modules are for meshing, for CFD, for FEA. There is also acoustic module for simulation of acoustic properties of flows. There is optimization module which helps engineers to run simulations in large or small in loops, which and iterate with the results towards the goals, and also other modules are on the way. TCA is extremely flexible. It's ready to be used in an existing environment or in for new users. So there are very many of usability options. TCA is unlimited. There are no limitations on number of users, job scores, so you can be sure that the users will use their resources to the fullest. It's based on open source. There's more than 60 open source projects included in TCAE, and we are ready to really use or make available what's available on the open source market to professional users in the industry. So it's our main business and main added value. Also on top of open source packages available in the market, we have invested more than 50 man-years of consistent development in a team to deliver this TCAE. So I guess the value of TCAE is obvious. TCAE is accurate. It can be used as a black box, or it can be used as a highly sophisticated, high-end software where the user takes all the decisions step by step. So it's always up to the user how deep to go into the rabbit hole or not at all. There are various options and ways how to use TCA. It can be used on laptop or on personal computer or on cluster or cloud or remotely from home or in Windows, in Linux, in batch mode, or in graphical interface. So there's really a wide range of possible usage. We have available 15 benchmarks which are publicly available, can be used again and again transparently. There are more than 50 real tutorials based on real projects from our consultancy business, and we have really good technical support. The new release has been released some time ago, and the cornerstones of the future development is the optimization tool, of course, the opt, then the acoustic solver, and the new simulation module we are working very intensively on at the moment is called T-Base, which will help users to create their own surrogate models and work with their data. Yes, and this will be it. I was very much concerned to be in those 5 minutes which I just made. So I will start with the content. So I would like to recommend to every user with every engineering project to start with goals. Really, it sounds like a cliche, which is everyone says that, but everyone knows that, of course. But I really recommend to sit down, grab a coffee, and think about what are your goals. Goals are extremely important everywhere in society and in life, and especially in engineering simulations. You have to know your goals because you have to know where are you going. Unless you will never get there. So goals. You should think about what's your project nature, where it comes from, where you want to go with it. If your project is disposable one-off or whether you are creating a workflow, a long-term process. That's extremely important. You should know what are your expectations, what you expect, where your project takes you. Will it be shared with your colleagues, or is it just for you? Will it be repeated again and again or not? What's the measure of your success, of the success of the project? When it's successful, when it's not successful, And how do we learn? We are there. We made it. It's finished. Again, very important question, because typically all the engineering projects or the engineering simulations are done in iterations, and you can iterate and iterate, and you can always improve everything. And it's very important to know when to stop, when the solution is good or good enough, or when not. My very favorite talk is about the accuracy. So you should definitely you should know what is the accuracy you want to achieve, and what's the cost, what's the effort you're willing to spend to receive this accuracy. It's a very important thing. So always think about what is the accuracy you want to achieve, and what's the effort you would like to spend, what are the resources you would like to spend. This is my very favorite graph. It's not favorite because I created it, but it's favorite because it's true, and it tells pretty much a lot. It tells that the effort is growing exponentially with the accuracy. It means that with relatively few decisions, I say those are specific decisions, specific qualified professional decisions you have to make. You should be accurate with your decisions. So for example, with a few decisions, you can very quickly get to some level of accuracy, right? But then if you're adding more and more effort, you're improving your accuracy only very little, right? So the effort grows exponentially with very little growth of the accuracy. The plot means the plot shows for example, the blue line shows how accurate you are with how many decisions have been taken. So for example, if you take only 10 professional decisions in your projects, in your project, you are going to something like 10% of accuracy. Of course, it's a general graph, right? It's general graph to give you thoughts, to give a food for your brain to think about. By the way, accuracy means here the distance from the measurement. Basically, you know the game we play here. You know the rules and that you also know the joke that everyone trusts the measurement, but the one who did it, and no one trusts the CFD simulations, but the one who did it. The measurement is holy grail. So this holy grail we are chasing here is the measurement results. Take it or leave it, or take it or not. That's what's going on, and we are pretty cool with it. So the measurement is the exact results, and you're getting closer and closer with your accuracy in your project. But yes, there are specific decisions, professional decisions you have to make, you have to resolve, and problems you have to resolve. And after some time, if you're like 2% close to let's say to the measurement, and you want to get 1% closer, you have to take really you have to improve a lot of things to get there. So it's really exponential, and you should know it's exponential, and you should think about it in this way. Okay, so accuracy versus effort. Always know your effort and always know your accuracy. Okay, I'll start with I'm in the middle of general thoughts about how to run simulation projects. So you definitely, if you're using finite volumes, you need to create the mesh, the simulation mesh. And here are some thoughts about that. So first of all, you have to have simulation ready geometry, which was the last webinar about. So I'm not going to spend much time about this topic. I only say I have a general case, which is a standard, very the simplest possible tutorial for TCAE, which is carved pipe. Sorry, so this pipe is a pipe, and where the flow flows through. So I can only show you that the simulation ready geometry is something like this. I will disappear the FEA and FSI part. We do not need it here. And in this example, I will just take a look and show that almost every engineering simulation project, a CFD project, has some combination of walls, So it has a wall, a rigid wall where the fluid flows in if it's internal aerodynamics, and external is similar, but we are talking here about the internal aerodynamics. But it's very similar, and there are some interfaces, typically the inlet and the outlet, right? So you have inlet, you have outlet, and the wall, and this is the what we call simulation ready geometry, because it's a one component, so we call them components. The volumes or later future volumes we call them components, and you can play with the components. You can have many components connected with the interfaces. This tutorial is rather simple, so I have only one component. It's a carved pipe with the inlet and with the outlet. And technically, it's STL file, it's surface file, which has been exported from some CAD, engineering CAD system. So this is what we call simulation ready geometry. It's important that the geometry is watertight, waterproof. So it means there are no big holes, or preferably no holes at all in the geometry. So the flow could stay in, and we can prescribe the correct boundary conditions everywhere, and that makes the that makes the simulation complete, and we can run it. Okay, so you have to have simulation ready geometry, which was about which was the last webinar about. Okay, so then you would need to start with the mesh. You have to have the mesh, and that's a process. You will split your basically volume into little pieces called cells, which helps you to run the simulation on it. So for such a case, I can show that we have system of components here. In other software, it would be similar. I have just one component, which is called pipe, and I say it's static. Nothing is rotating, nothing is moving here. It's really static, solid component. And yes, it has one wall. According to the STL surfaces, it has the outlet, it has the inlet, and for that, I'll take a look what I have in the presentation. I have to create full mesh for all components, yes. And yeah, for the mesh, I have to set very important thing. If we use, and we recommend it, but we never push it, but we recommend it. We recommend the SnappyHex mesh, which is highly compatible with TCAE and with OpenFOAM, and it's really useful. But again, we only recommend it. We never push it, so it's always up to the user whether he or her just load the ready-made mesh, a complete mesh, and start computing directly on the mesh. TCA is ready for that. Or if you are creating the mesh, so we suppose the simple case, the typical case, that you create the mesh from scratch here. So we have a component which is consisting of watertight STL surfaces, and these STL surfaces are the volume is meshed in the volume with the background mesh, and you say how many times the background mesh is refined with respect to the surface, or and how many boundary layers are considered in the case. So you can say it here. This is just a basic principle. You can refine the mesh, of course, many times, and sometimes you need to specify the point which is located in the mesh inside the component, which tells the mesh solver what's the inside, what's the outside, and that's something like a general principle. So we did in this pipe case, and couple of comments. The mesh size is super critical parameter and super critical number. So the size of the mesh, the number of cells that your mesh consists of, is extremely important factor on everything. It influences the speed of convergence. It influences the quality of the results. It definitely concerns everything, and especially the amount of data and the simulation time. And simulation time is something which is one of the bottlenecks. I would say, if you asked me, the biggest bottleneck in engineering simulations is getting simulation ready geometry. The second biggest bottleneck is simulation time. Simulations take time. big simulations, transient simulations, multi-phase simulations, accurate simulations, they all take quite a lot of time. We have to get used to it, and we have to know what we are doing and save every time and every resource possible. Let's take a look what next we have here. See, I always recommend in every project to start with small meshes. Play it small, play small game and play iterations and do a lot of iterations in the beginning, because you can always refine the mesh. It's very simple to refine anything, but it takes finer meshes take so much more time and effort and resources and everything. So again, go in iterations, start with iterations, because every engineering project typically is used in an iterative process. That's normal because you always improve everything. But start small, start with small meshes. It saves you tons of your time and also gray hair. Yeah. So it's this. Okay, it was just quickly on the mesh. I can what I can say, okay, we have some settings here. I can completely remove everything from the case, and I can ask the mesh solver to create the mesh. So it's going on here. It tells me yes, it's meshing now. The meshing process is running. It takes only a little while, so we can wait for it. So when the mesh is created, I can visualize it with this button. Yeah. Let me check. Okay, I will ask again. Can you show me the mesh, please? And what? Yes, it's here. So this is the mesh of my basic settings. So we are already looking at the mesh which has been created in the tmesh module, which ran basically all the necessary settings, writes everything down and run block mesh and snapx mesh on it. And yeah. So on my mesh, I'm clicking. I don't know why it's so slow today, but okay. Fair enough. So this is my mesh. This is already volume mesh, which will be the object of my simulation. So it's quite rough, but I'm okay with it because it's relatively quick. So you have to have the mesh. And in today's webinar, Radek will show much more about how to set up the mesh, but I only say a couple of principles in the beginning here. To the mesh, it may look complicated, but it's not. Almost everything can be automated. Almost everything can be used again, and good. It's like neural network, right? You can use the best things in the future because you remember it, and it's the same. With riding a bike, no one is the best when rides the bike the first time, but next time and next time and next time it gets better and better. And it gets quickly better unless you drive or ride it. Without knowing you're actually driving it. It's the same with CFD simulations. There's always a huge chance that you will repeat the good positive outcomes and tips and tricks. So what looks difficult, it's not after some practice and experience. Okay, I'll just quickly comment on simulation setup. I will just quickly ask my colleague Radek if I'm still visible and you can see it and follow.
Yeah, definitely. Just
And
continue.
does it make any sense, the presentation so far, Radek?
Yeah, definitely. I'm
Excellent.
making a notes and I will follow your steps
Yeah,
during my part. So
okay.
perfect.
That's encouraging. Thank you. And I will just say a few comments on simulation setup. So yes, again, you should think what are the outputs, right? What are the particular results you want to make out of the simulation, and all the rest of the settings is depending on what are your outputs, why you are doing. It's similar to goals, right? But with outputs, we mean here really the exact numbers, if it's efficiency or if it's pressure loss or if it's some torques or some visual expected or unexpected flow fields. So it's always important to make sure you know what you are going for, and in the phase of simulation setup, to make the case ready for that. That's very, very, very important. You should decide, for example, what are your time options, right? So with time options, I mean, what's your, in the CFD settings, what's your time management, right? Whether you're going for steady state simulation, or could go for transient simulation, or you can go for both. You can initiate the transient simulation with the steady state simulation, and how many simulation points you want to simulate. With simulation point, here we mean a set of boundary conditions applied to the that lead to different results, right? So you can have, for example, in this case, I have 3 points. Perhaps I have 3 flow rates, 3 different flow rates. So the different points create characteristics and speed lines, for example, if the speed is the differentiator. So you should always make sure what's your time options. Extremely important. I would say it's perhaps the biggest simulation setup choice, your time options, whether you're going for steady state or for transient. In my case, I'm here going to do a steady state simulation, but in some cases it's necessary to run transient where the quantities change in time. Okay, the next thing is settings that concerns physics, solver, and turbulence, and similar stuff. So you should know what to set. Physics is absolutely important. So you should be able to say what's your fluid, whether it's incompressible or compressible, what's the reference density, what's the reference temperature, what are the reference environmental physics. Of course, you should decide the solver, of course, the numerical order, the quantities, the number of processors you are going to run, and sometimes down the chain you should decide the turbulence, what will be the turbulence model, what would be the turbulence approach, and that's a very typical question to solve. What's very, very important is boundary conditions. From our technical support over 15 years, we know that 80% of all errors are somehow connected to boundary conditions. So boundary conditions are extremely important part of the process. You should know what you are doing with your boundary conditions, and if they're physical, if they're relevant, if they're telling you things, because as you know, in CFD engineering projects, it's extremely important what's on the surface. In the volume, you have limited options what you do in the volume, right? Because the volume is the playground of Navier-Stokes equations. So the equations are set in the nature. So the volume is the volume is Navier-Stokes equations. Of course, you can set the dynamics in density and viscosities and everything, but that's the volume. But your real input is on the boundary conditions. Really, if you should remember one thing from this webinar, boundary conditions are critical everywhere. So it's important what you set on the wall. It's for every quantity. It's important what you set on inlet for every quantity. It's very, very important what you set at the outlet of your simulation domain for every quantity. You should decide what will be your post-processing in this phase. It's really important to know what to set and how to set in the beginning, in the setup phase, right? Because afterwards some information may be lost, right? Because not everything is being saved during the simulation for good reasons. We know everything, but we never save everything. So you should know what to save and what not to save. Yes, CFD simulation is typically an iterative process, right? Of course, if you are in a research mode, right, you're researching things for the first time, of course, you always go in an iterative process. Sometimes later, as our clients know, in the production, you do more and more productive simulations and use it for your products, and you just run it as a tool. But not every time it's the case, but almost. Oh, not almost every time is endless possibilities what to improve in every simulation. It's never done, right? Simulation is never like finite process. It's a system which can be always improved, always something you can always do something better than last time. So you typically run iterations here. In iterations, I mean iterations in running, run 1, run 2, run 155, and small meshes help. Small meshes help you to iterate quickly over your simulations and improve quickly. You should always, during the simulation, that's important, during the simulation, you should follow the basic laws that conserves. So the flow rates should conserve, the residuals shall ideally drop, and final results can be also followed. We can maybe show it, right? So if I run the simulation of which is this CFD, it's this. Okay, I will run everything because I'm not sure if there are several steps. So I have run all run process. So now it's running, and I guess yes, this case is a little bit special because it has also FEA part. So there's the outer part, which is a coating of the pipe, which is meshed with NetGen, and the forces are transformed to the surface, and we can compute the material stress and deformation. So it's a little bit more complicated, but still I see something is going on here. Yes, so the case is finally running and iterating. So we could show another window of view. So I could be interested in, for example, in line chart view, I would be interested in some quantities, additional quantities that are processed during the runtime, and we could take a look, for example, how the, I don't know, pressure drop looks like, for example, and okay, maybe why not? Yes, so this is okay. It's quite flat. It's quite flat in this case, but we could zoom things a little bit, and this is how the simulation. Actually, the simulation is done already. Okay, so we have 3 points. So okay, no, the third point is going on here. So the third point, let's catch it. Let's catch it. I'm going for it. I'm going for it. Yes, here you can see this is the delta P total. So the difference in total pressure compared from at the inlet and to the outlet, and you see it's somehow hopefully converging. It's simple tutorial, so you can display things here. You can 3 sets of residual. You can see 3 sets of residual here. Yeah. So again, things may look complicated for the first time, but they are not. You should be patient and really learn along the way. And look what we have here. Achtung, there's an expert on the air, and I will ask Radek to hand over the presentation. I can switch. I will switch it.
Okay, thank you.
Okay, I will switch. I'm still not very much used to. Yes, you did it already.
Okay,
Okay.
I think you can see our
We can
webpage,
see your
right?
screen, Radek. Please
Yeah,
go ahead.
perfect. Okay, thank you, Luboš, and I will smoothly continue with a uh, thorough explanation of all the points of the workflow, including the meshing and CFD simulation. And let me follow up the previous webinar. Just for those who haven't seen it yet, you can go for the resources webinars on our web pages, and here you will find a link to the recording of our previous webinars, so you can follow it. And I will smoothly follow up the the previous webinar. So what we did, just a small recap. We take this small Kaplan turbine, the real solid shape of the housing, of the motor, including all the solids, all the parts which are not necessary for CFD simulation. So what we did the last time, we cleaned it. So what we have done, we get rid of all the solids and unnecessary parts, and we extracted just the wet surface. And also we have created the interfaces between rotor and stator, and between the extensions, for example. And then we have exported, generated, triangulated the surfaces, and we have exported the STLs. So today I will take this STLs. So I have put it here into this directory, and this STLs will be used to import and to create the simulation flow domain. So just to see the overview of all of them. So basically we have set of STLs exported, and what we do is that we use each set of STLs to create the set of components. So we will have more components to build our flow domain. So in this example, I have also generated this huge or large extension, which is somehow also useful to let the flow calm and to have a proper conditions, and for example based on the measurement or the setup. So for example, you just know the pressure at some points, and also with respect to the evaluation purposes. So for example, you would like to have evaluated the efficiency just starting on this elbow and ending on this outlet cone, what and etc. And also this will create additional components, and more components, more fun. So let me start creating the project. So I will start very from beginning, like you are starting the new project from very beginning. So I will open TCE, and I will create a new project. So I will click here on new, create empty, and directly I can store the project on somewhere on my disk. So I will put it into this folder we will be working with today, and I will name it, for example, TCE webinar Kaplan. So I will name it as this, and from now on all my setups will be stored within this folder on my disk. So first of all, we need to start to setting up the mesh. So let us follow Luboš notes or Luboš items which he had presented. So first of all, let's somehow tell about the interface. So what we have here, we have the main project manager, we call it, which holds all the managing buttons. So to work with and to run the simulation, generate meshes, generate reports, etc. And here we can enable all the modules. So today we will work with the tmesh to setting up the meshing parameters, and whenever we will have the mesh and we will be satisfied with the mesh quality, refinement, etc., then we will start to setting up a CFD simulation. So let's go for it. Let's go for tmesh. So if you click on the tmesh, then you have new set of menus to set up the meshing. First small menu is the general. Here you choose what will be the output. So we will work just with the CFD application. So we are fine with the CFD mesh, but in the same way we can set up the FEA mesh or both. Here use external geometries. If you check this, then instead of loading the STLs into the project, you just tell the path to the STLs, and the STLs, the input geometry, will live outside the project. So whenever you move your project somewhere else, you need to move it together with the input STLs to, for example, create a new project or resimulate something. Otherwise, you will lost track with the input geometries. So if this checkbox is unchecked, so then the STLs are imported directly into the project and it lives within the project. So you can move the project anywhere, and all the results and all the information remains within the project. In general, all the modules can be scripted. So maybe we can also do a webinar in the future about the scriptings. So using the scripting, you can modify the workflow in the thousands of ways. So it will give you more space and more options how to modify, how to include a specific functionalities which are not directly implemented, or your codes, or any treatment or modification of the geometry, meshing parameters, or whatever. And it also holds for the CFD simulation or any other module. So we keep it in this way, and now we can go to the CFD mesh, and let's start with the first menu. So here, this is the rotation reference frame, because we are working with the the rotating machinery. So we need to define the rotation, and rotation is set by the axis of rotation. We have two, static and rotating, because also we can have a stator which has some rotational symmetry, like for axial machines. And whenever we have any periodic boundary conditions, this condition needs to know the transformation with respect to the rotational symmetry. So therefore, we have typically two reference frame. One is called static and will be used to define stators, and the second one is the rotating, to define the rotating regions and the rotation transformation. If I remember correctly, yeah, the rotation axis is Z. Yeah, so the blue arrow here denotes the Z axis. So we will modify it to Z axis rotation reference frame. And I think, yeah, our geometry is placed into the origin, so the rotation axis goes to the origin. Okay, so this is rotation reference frames, and now we are going to components. So now we will set component by component. So basically, each component is meshed separately, so we can treat any component as a separate mesh. So we need to just focus on each component, mesh it, check, for example, if the mesh is correct, and then go for the next component. Whenever we have all the components set, then we need to take care about the connections, about the interfaces, and if all these are checked and generated, then we are done and we can go for CFD setup. So let's go with the component by component, and let's start importing the STLs. So let's go with the first component, which was the inlet extension. Inlet extension is just the pipe. So we have inlet extension inlet, we have a wall, and we have one interface which will be connected to the stator. So we have these three parts. Ta-da! We have it. We have it here. Whenever you load these STLs, it will appear in this table, and also it will appear in the render view. Anytime you can click on any part to see which part we are setting up if we are not sure. And what is also good is to click here, because the CFD geometry is held by this item. It can be hidden, it can be shown. And what I like is to set some kind of opacity, because if there are some object inside, I would like to see what is happening inside. And also, for example, for setting up internal point, which defines part of the meshing. So then it's also good to have the opacity to see if the point is put inside. So for each component, what we can set, so we can set a component name. So it's up to the user. For example, I can name it as inlet extension. Reference frame, static. Periodic geometry is in case we have just kind of, for example, periodic segment. So in some scenarios where we expect the symmetrical behavior of the flow, we can save some cells by cutting the axial domain like a cake. So we put just one part and preset periodic boundary condition, for example. But in this case, we will have it as a full pipe. So what we have here, type of the boundaries. So inlet. So we have a set of boundaries. I think for CFD engineering, it's pretty clear. At least if you are doing internal flow, you have to have at least one inlet and one outlet from the domain. With respect of the component has to have some inlet and outlet. So if the patch is connected to the neighboring component, we call it interface. If it's not, we call it inlet or outlet. So inlet extension is the inlet, wall is wall, which is the default type, and interface outlet interface from inlet to the stator will be the outlet interface. Yeah, the naming I think is natural, that inlet denotes the part where the flow goes in, outlet is part where the flow goes out, and free stream interface is where we don't know the direction of the flow, or there could be in general both directions, something like if you have the propeller behind the ship or ship vessel, and you just need to put the propeller into the rotating cylinder, and the whole cylinder is the interface. So you can't, so there can be both direction flow on this cylinder. So for that scenarios, we set the free stream interface. But here we have the outlet interface, because this is just the extension to initialize the flow. We don't need to solve it as too accurate. So for example, we can keep all the refinement surfaces to minimum, and what we need to set is the background mesh cell size. So this is the largest cell which will be created. So I will typically we use the cube cells, but for example, I can show you how to save some cells on these extensions. So first of all, I will do in this way. I think the diameter of the pipe is something like 16 centimeters. So if I set just 10 centimeters, it's too large, as you can see. So let me start with the, for example, 1 centimeter. It could be, yeah, it could be fine. And following one of the Lubbock points, always start with a rough mesh. So make the mesh as rough as possible, but the mesh refinement has to be set in the way that all the topological shapes and all the details has to be captured. Yeah. So typically, if you do such a large meshing, I think it's not a good idea, because you will have just one cell or 2-3 cells. So I think it will be not possible even to mesh, but it must be some, to certain level, it must be accurate and well resolved. So let's start with 1 centimeter. For example, if you would like to save some cells on this part because it's not so important, you can uncheck the cube, and now you can set the dimensions of the basic cell size in any direction. So let's start, for example, with in, I think this is the y direction, right? So we can make the double, for example, in this direction to save some cells. Okay, and the last important parameter to set is the internal point. So internal point is visualized by point. It's interactive, so you can take it and push it into the internal part of your component, or you can define it manually. So let's say I will adjust this diameter is just for the visualization purposes. So it will visualize just this sphere, which is nicely draggable, and we can push it or put it into our domain, or you can put it, of course, manually if you know the coordinates or dimensions of your components. Okay, so I will get rid of visualization of this outlet interface. So I think I am done here, so I'm okay with that. So I can I can I can disappear the internal point just to accidentally, I don't want to accidentally move it outside. And now, for example, if you have the first component set, you can save the current setup and just quickly you can build a mesh. Okay. Now, if you see it, okay, there is some troubles with my setup, so I can click here, check, and I think it will tell me, yeah, that I have the outlet interface which is not connected to any other component. So if I need to mesh it from now on, I can set it as outlet, go back, save my current setup, and now I can build the mesh. If you click here on the table TCA output, you will see what is happening. Now, yeah, the mesh generation is pretty quick because there is almost nothing to do. Just create a background mesh and make the snapping. So if I show the mesh, as Lubos already shown us, surface with edges, so we can see the basic mesh refinement. So it's pretty rough, but the mesh is okay for the simulation point of view. From the accuracy point of view, of course, it's not the optimal, but for the first check if my simulation will be set up in a proper way, and if at least some results I will get, it's enough. And also for the webinar purposes, because I need to run the simulation quickly within the webinar. It will be pretty boring to wait, for example, 1 hour for the results. Okay, so this was the first component, and in the similar way, we are going to the next component, which will be more interesting. So let's visualize back the CFD input geometry. I will get rid of the mesh, and let's import the parts for the stator. So let's take all the stator parts and the interfaces. So interface from the inlet extension is this one, and the next neighboring component is the rotor. So let's pick this interface stator rotor STL. All right, perfect. So new set of STLs for the second component is loaded, and now we can do the same framework. So set all the parameters. So I can name it stator. Reference frame is still static. I don't need any periodic geometry because it's a full geometry. And let's go for the types. I will go back to component 1 now because it will be already connected. So I will click on the outlet interface, or I will set outlet interface. And for component 2, I will quickly set the type. So what we have here, interface inlet. So this is the interface inlet interface to stator to rotor. So to be able to mesh it before I add additional components, so I will set it as outlet. The other, I can keep it as a wall, or if for some kind of, yeah, I will keep it for sake of simplicity. I will keep it as a wall. Stator hub, everything is wall, and yeah, so the rest are the walls, rigid walls. Reference frame here, let's check. So this shaft which goes through the stator, so the stator is, I think, adjusted to the casing by the blades, and the shaft goes through the inner part of the stator to the rotor. So this shaft part, which it is physically rotating, so I can prescribe the rotating part outside the rotating component. So this can be done for all rotational symmetry parts or walls or patches. So in this way we have just this shaft, so we can prescribe rotation on this shaft within the stationary component. Now let's go for the refinement. So first, because before I will go for the refinement levels, let's set the background mesh cell size. So again, I will put as 1 centimeter, which was fine for the previous component. Now I keep it as a cube, in a cube shape. Okay, meanwhile I can directly put the internal point into my component. So let's check if, okay, it's too close to the shaft, so let's put it a little bit further, and yeah, now the point is inside. Perfect. And now let's go for the setting up the refinement. The refinement means, if I visualize the background mesh cell size or background mesh visualization, so every cells which will be intersected by one of these STLs will be refined up to the level we preset here. So let's go for it. So here we have the same refinement level in Z and Z and X coordinates. So the inlet interface, we can keep it in zeros. Okay, then what we can refine, for example, all the other parts. So let's go for the important parts. So let's set everything to level 2. Okay, and maybe this inlet duct we can also keep, for example, we can set to level 1, for example. Then what we have there, we have blade pressure suction side. So let's see what will happen if we keep it in at level 2. And for example, blade leading edge, which is these small parts of the blade, which is highly curved. So for those parts, we can set higher level of refinement. And because they are small, we can keep the level same for as minimum and maximum. The minimum and maximum refinement level, if we set different values, for example 3 and 5, so the algorithm decides what level to put at the different parts of these STLs based on the local curvature. But in this case, because this part is curved as a whole, so we can set the same level of refinement for the whole part. All right, so I think we can keep it in this way, and let's try what will happen if we start meshing it and how the mesh will look like. So again, I can go back to the manager, I can click save to be sure that everything is correctly set. We can click the check. So project setup content again, interface. Yeah, perfect. So I have created the interfaces, but I haven't connected them yet. So the connection is done by right button click on the given interface patch, and then the menu will appear and it will give you a set of possible connection, and we have only one possible connection now, is to connect to the stator interface. So now it is connected, and the connection also can be checked here. If you go a little bit further in this menu and scroll down, and you extend this components map, so it will tell you how each component is connected to the other components. So now we have nice solid connection from the inlet extension to the stator. All right, so now again save my setup to be sure. I will check project setup is okay, and because I have changed the type of the boundary to the interface, so the first component has to be also remeshed. But we are fine because we haven't changed any meshing parameters. So now I will focus just on the stator. And what I haven't done, so anytime you can abort it, and to speed up the mesh generation process, you can also parallelize the meshing. So if you go back to the setup, to the last menu here, parallel run, you can increase the number of processors. My computer here has 10 physical cores, so I can set 10 cores. Again, save my changes and rerun the mesh generation process. Again, if you go to the TCA output, if you set here output messages, you see what is happening on the background. And for more detailed output for the currently running task or solver, you can see the output. So this is the output of the SnappyHex mesh. So for those who are familiar with the SnappyHex mesh, you can follow all the log, all the details of the meshing. So now the mesh is almost done. Okay, and something was wrong, so maybe all right. As you can see, the mesh leaked out, so probably I forgot to include some part of the setup. So what I done. Okay, so I have all the parts, I hope. So this is the shroud, this is the shaft, inlet duct is okay, stator hub is also there, stator blade, blade suction, part pressure side, leading edge, interface rotor stator. Alright, so now I'm not sure what happened. So the internal point is still inside, which is okay. Okay, the refinement was also fine. Okay. So, okay, so to be honest, I'm not sure what happened. So typically, what does it mean if you see such a leakage? So if you visualize the mesh again, so it means that the mesh was meshed from both sides. Yeah. So if I go just for the mesh and here to the multi-block, and I will just pick the boundary, so you can see, you can visualize each part of the mesh. So we have it there, but also we have this default patch which points that the mesh leaked out from our domain. So which means that the domain is not closed fully, or some kind of meshing parameters like internal point is put somewhere else than it should be. But in this scenario, I am not really sure what happened. So maybe I have accidentally took the different STLs. Okay, let me quickly check. So the inlet duct stator, right. So what I can do is to visualize my input geometry, and for example do a slice if I have enclosed counter. So what I can do is to make a X slice, for example. Yeah, this one, apply, get rid of the CFD. Okay, so I think everything is closed, right? If I get rid of the first one, okay, all right, it seems, yeah, it seems fine. Maybe, I don't know if the export was okay. Okay, so interface rotor to stator inlet duct, or maybe the mesh, because, okay, let me try it to make it a little bit rough, because I'm not sure if I took a proper STL. Maybe if you can see it, I have some troubles here, so I'm not sure if I took a proper STL. So we have some local, yeah, if you can see it now, we have some holes in there. So maybe I took a wrong STL, but let's try to fix by a little bit, make the rougher mesh. Just as an example. So let's regenerate the mesh with a little bit rough setup, but the main point is that I should go back for the STL generation and check what happened here, right? Why this, you can see these holes at this surface part. Okay, let's check if now the mesh will be better, and if not, maybe we have some other option how to heal it implicitly, but let's wait for the result. Okay, all right, and now it's meshed properly. Okay, so there is some trouble. Okay, go back to the multi-block inspector. No, sorry. CFD mesh and visualize the whole mesh. Okay, so now it is correct. So I have some troubles on the input STL. So definitely when I will go for the refinement, I should recheck the input STL and heal the errors in the input STL. So okay, so this was example how to tackle with some errors in the input geometry, and this again emphasize what Luboš mentioned, that the crucial part is to have ready for simulation STLs as the inputs. Okay, so this was nice example, an unexpected example of the bad STL meshing quality or STL quality. And I will quickly go for the other components in this example. So let's go for the rotor. So again, I will import the rotor STLs. So interface of the rotors and STLs of the rotor. Let's import them. For now, I will get rid of the CFD mesh, and I will show the CFD geometry. So now we have this part. What I can do again is to set the component name as rotor. Let's go for the interfaces. So this is the rotor outlet. So I will set for now as the outlet. Here I will set it as outlet interface for the stator because I can directly connect it to the interface from the rotor side. And now right click, connection to the stator. And as you can see now we have nice 3 connected components. I will keep all as a walls, and reference frame here I need to care mainly about the wall boundaries, and here so all the walls here like hub excluding the shroud will be rotating, so all these parts which creates the impeller should be rotating, but the shroud is static, right? So it's so-called unshrouded case. So shroud is not rotating, only the impeller and steels of the rotors are rotating. Before I go for the refinement levels, I will again set up the cell size for the background mesh. And for example, because the rotor part is the most important part and the main flow patterns are happening there. So for example, I can set finer refinement or finer cells on this level to have also the finer cells in the volume, not only on the surfaces. In the same way, I need to set the internal point. Let's put it inside. So just if you are putting it manually, so just you need to change the views to adjust the point in the inside the rotor part. Just check if the point is not, for example, in the hub or in the cell in the blade. But I think now it's pretty much okay. Yeah, here between in the flow in the blade passage here. Okay, so it's placed properly. and go back for the refinement level. So what I like is that the mesh refinement on neighboring interfaces is homogeneous, or not homogeneous, but has the same sizing of the cells. It makes sense because you interpolate, or internally the quantities are interpolated on these pair of interfaces, so it makes sense to have the same refinement from both sides. So on this rotor stator interface, for the stator part, we have level 2 and 2. And because we have refined the overall cell size twice here, so we have we set a half of a cell size on the stator side. So I can set just the level 1 because it will be comparable. It will have a comparable size from the rotor side on the interface to the cells on the interface from the stator side. Again, for the blades, let's quickly set, for example, as an example, I will set level 2 everywhere, or maybe, oh sorry, because I have set the half of the cell size on the stator part, so I will set everywhere 1, including the hub and shroud. Okay, and let's see what will happen. Just as an example, that if this refinement will be sufficient to mesh the rotor section. And I hope I set everything. Not, I haven't. I forgot to set the reference frame for the whole component, which is important for rotating part. So I'm setting it as rotating. Okay, now let's click save. Let's try to run the rotor side meshing, and whenever it is done, let's visualize it, and I think we will see that the mesh will not follow all the detailed part. So this is crucial when you are starting. Whenever you generate the mesh, immediately visualize the mesh, because it will tell you a lot about the meshing. So as you can see, there is a bad refinement level for meshing this gap between the rotor and the stator and the shroud. And for example, to see the overall meshing for the blades, so you can again click on the CFD mesh. I will get rid of all parts and I will show just the parts of the rotor. So for example, or blades and the hub. So you can see both that the leading trailing edges are not well resolved, and the main problem is that the gap between the blade and the shroud is also not well resolved, and you can see such flaws in the mesh, which generates a very bad cell parameters, which can finally, during the simulation, which can lead to the divergence or crash of the solver. So we need to go back and we need to refine the given part. So let's say I will just refine the leading and trailing edge. So I will increase the level of refinement on the blade leading edge or on the blade trailing edge. Therefore, if it's possible during the STL generation, it is good to split really these parts into separate parts. If it's possible, it's not crucial, but then it will help you and give you more freedom in setting the refinement locally. Yeah, otherwise, if you have one STL for the whole blades, then you need to set, for example, the levels like 1 as a minimum and 2 or 3 as a maximum. And then, of course, the solver, the engine, the meshing engine will decide where to put the lowest level of refinement or the highest. All right, and the last one is the blade cap. We have also splitting of the blade cap, so now we can set level 2 for the meshing the blade cap. Going back, clicking on save, and regenerating the rotor mesh. All right, so this is the standard scenario of mesh generation for the new geometry for your new project. So go step by step. Let's start with the rough parameters, low level refinement, high sizing of the cells, because you will get the mesh quickly. You will be confident, or you will learn the shape of your input geometry. It will show you where the problem could be during the meshing. And oh, sorry, I click build. I need to click on show. So now what you can see that, okay, so the leading edges are better, but not the best. But I think that still we have the problem on the shroud. So if I click on the CFD mesh, and I will also visualize the shroud. So still we can see that, yeah, there are big flaws and bad regions, bad cell regions in the gap between the blade and shroud. So again, I will for now I will just increase the level of refinement for the blade cap, and I hope finally we will have a good mesh which we can use for the simulation. So let's run our last iteration, and if the mesh is okay, then we can add the last component and we are ready to go for the CFD part. So as you can see, again, you need to iterate, you need to go step by step. What is good that this component thinking will give you a focus on a certain part, and you don't need to take care about everything within one shot, but you can go step by step over over each component. And right, so as you can see, okay, I will here, if you click on this icon, it will reset the view and also reset the view rotation point. So sometimes it's good to re-click this reset view button. So if you can see now, there are no holes in the shroud. So it means, I think the better visualization is that if you get rid of the surface with edges and visualize just the surface, and now you can see now a nice smooth shroud without any problem. All right, so I think the rotor part is fine. And last but not least, maybe just to speed up, I will just add the outflow, and I will be not adding the outlet extension. So let's go back to the T-mesh. So let's go here, and I will add the last component, which will be the outflow. Import, and let's go for the outlet. So outlet hub, outlet wall, and interfaces. So interface rotor to outlet, and the last one will be the interface outlet to outlet extension, but I will set it as a final outlet. So this will be pretty quick. So you can see the extension just includes the interface, the hub part of the rotor, and the outlet wall. So this part is static. Interface outlet to outlet extension will be the physical outlet. I will go back to component 3. The outlet I will redefine to outlet interface. Rotor outlet is the inlet interface. Immediately I will connect it to the rotor, and hub and wall are the walls, but the hub is connected to the rotating impeller, so I will set it as rotating. The background, my cell size, I will set back to, for example, 1 centimeter, and I will refine just the hub. I will refine the inlet interface to the same level as on the rotor side, including also the different sizing, of course. Therefore, 2 outlet wall, I can keep it. Okay, I will set 0 just for speeding up the simulation. I think it will be okay, and the outlet will be also not refined, so it will it will have the dimensions of the background mesh cell size. The last what I need to put is the internal point. Okay, it is directly at the outlet, so I need to move it a little bit inside. Nice. And I hope everything is set, so let me check. So I will save. To be sure, I can click check. Okay, connection is done properly, and let me build the last component. And whenever this component is also meshed properly, we can, for example, we can generate all the components again, or all the components which were changed, because I have changed the outlet to the always to the outlet interface, so therefore I need to recompute it. But I will do at once at the end of the T-Mesh workflow. And okay, CFD mesh is yeah, it was here. Sorry, what I have clicked. Yeah. Okay, maybe I need to go to the multi-block. Sorry, because I have clicking a lot here. Yes, of course, and I will click on everything just to see all the parts, all the visualized parts. And okay, but now, right, I visualized already all the parts generated, and when I visualize it as a surface with edges, nice, so we can see, okay, it looks good. There is no flaws in the mesh. Just to be sure, I can make a slice what is happening inside, just to see also the volume inside on the slice. Again, surface with edges. So here we have our topology. So okay, what is important, that all the parts important are meshed properly, so it has its own shape, and we don't see any troubles, any holes in the geometry. Here we can see that also the gap is refined, so we have some volume there. So this is a good good setup for the first CFD simulation run, and whenever everything is running, then we can start refining the mesh and looking how the results changes to obtain the result with better accuracy from the mesh parameters point of view. All right, so everything we have done. So meanwhile, I will remesh everything to have also the final mesh, which is then on the background imported into the CFD section and used for the CFD simulation. All right, so this was the meshing, and now I can enable the CFD setup and quickly go through the CFD setup. So typically the CFD setup is much more simpler to set up from the time frame point of view, because we just set the parameters of the fluid, we set the boundary conditions, etc. So we don't need to iterate and waiting for the mesh generation. So this is what I meant. So let's go for the CFD setup. In the general section, we have the simulation type. All the simulation is always tailored to the given application. So here we have the application of hydro turbines of the Kaplan type. So we have a type here, hydro turbine. So we can choose this one, and this will modify some setups which are tailored just for the hydro turbines, and also it forced the report to include all the important parameters which are typical for hydro turbines, including the efficiency formulas, heads, and other quantities. Let's go for the physics. So in the time management, we choose the solver time management if we would like to go for the stationary or transient simulation or both. So for the initial simulation, we will go for the steady state, which is much simpler, faster, and for 80% of applications, it's enough and good and accurate enough. If you need to go for to resolve more complicated flow patterns at unstable conditions or whatever, then you need to go for transient. So let's stick with the steady state. Speedline is a set of simulation with a fixed rotation speed. So this Kaplan runs at 1500 RPM, so we need to have just one speedline. Speedline points mean how many different boundary conditions you would like to simulate within a single run. So typically if you need to resolve the efficiency map, so basically this number is the resolution of this efficiency map. So if I set, for example, 5 points, then the 5 points will be simulated and I will be able to set 5 different boundary conditions, typically 5 different flow rates or 5 different pressure boundary conditions at the inlet and at the outlet. The number of iterations, so it's the maximum number of iteration which solver performs. It depends again on the application, on the complexity of the of the machine, on the mesh refinement, and many other parameters. So typically, if you start refining the mesh, and if, for example, if boundary conditions are far from the best efficiency point, then you need to add or increase this number of iterations. So for this purpose, for example, we have a pretty rough mesh, so I will set 1000 iteration as a maximum for each simulated point. Fluid properties, here you set the property of the water here, or you can use some custom fluid parameters. Let's stick with the water. You can use fluid defaults, which are set to the water at 20 degrees Celsius, I guess. So if you need any additional parameters, you can adjust them here. Rotational reference frame. So here you set which rotational reference frame will define the rotation. So therefore we name it as rotating. So rotating component will be rotated and all the physics, and it will be modeled as rotating region. And here you set the rotation speed. So the units we can check, we can choose our RPM, and it operates at 1500 RPMs. Just a typical mistake is the direction of the rotation. So it follows right-hand rule. So if my thumb points along the z-axis, so my cross fingers show, define the rotation direction. So as you can see also from the blade definition on the stator, so in this way the impeller rotates. So therefore it's a positive value for the rotation. So the positive value is okay. Within the multiphysics, you can define some additional physics to be included into the simulation. So here typically for the pump and hydro turbine application, we can ask for evaluation of the cavitation risk. So it's just the post-processing tool which evaluates the pressure and compare it to the pressure of saturated vapor value. And if the pressure is below this threshold, this saturated vapor pressure, then it denotes these cells and creates some statistics above these measurements. What the parameters should be set. Cavitating patches means these patches will be used to evaluate how many proportion of the surface on these patches are affected by cavitation. So typically I would like to include all of them. Maybe I will just exclude the shaft. So I need to have all of them to be included in the statistics. The low pressure patch means the pressure at the lowest side, which is used for setting up other additional cavitation parameters. So typically for hydro turbine is the outlet. So I will set the outlet. interface, which is this one, and the high pressure patch is typically the inlet patch or the patch which is of the interest. So maybe I can set this elbow, the inflow into this elbow part. So it will be, for example, the second one. All right, so this from this point of view, cavitation is enough to be set here. Turbulence, you can choose any model you prefer and you are confident with for the given application. For the simulation, number of processor is the same like for the T-mesh part. Here you can adjust the numerics. So numerical order, second more accurate, less stable, first more stable, less accurate. But typical for this pump and hydro turbines application, the second is uh, is stable enough and will give us very accurate results. If you have some special format or special shape of cells, like from external tools, which have some high non-orthogonal property of the shapes, you can enable this non-orthogonal mesh schemes, which are more diffusive and keep the solver stable during the simulation. But it's application for this kind of non-orthogonal meshes. Runtime evaluated quantities. Here you define what you would like to see at the end of the simulation, besides the main quantities like pressure, velocity, turbulent quantities, and other. You can ask to evaluate some other quantities. The averaging window is used to average the solution because still even it's steady state, so every iteration can oscillate because of the property of the solution and the conditions. So it's important to have a nice converged, stable, constant solution at the end, and this averaging window is additional stabilization of the instant quantities. So again, it depends how big are the oscillation and how the case behaves. So based on this, you can adjust the averaging window size. By clicking here, you can simply enable what quantities you would like to additionally evaluate from the simulation. Efficiency probes define the quantities for the report, basically from which parts the torque will be evaluated, pressures will be taken, etc. So typically the inlet patch is the patch of the interest where you can measure or you would like to take the average pressure and other quantities. So for example, because this inlet extension could be some kind of artificially set just to initialize the flow at this part, so we can choose this interface, the second one. So basically this interface will be used as for evaluating the pressure at the inlet. Torque patches, typically you choose all the patches which are rotating. So basically all the patches here listed in this table or in this list. And outlet patch again can be chosen either the outlet or directly at the rotor, just to evaluate the efficiency of the rotor itself and exclude some losses of this diffuser or whatever. But let's keep the outlet as the outlet interface. Of course, you can add more efficiency probes if you would like to evaluate it from different interfaces, etc. You can also add some additional forces patches if you have some specific objects on which you can explicitly evaluate the forces acting on it. Then you can list it here. Just you will edit. You will choose on which patch you would like to uh, evaluate the forces and other quantities connected to the forces, and the probes. You just define the coordinate of the point in which you would like to follow the given quantities. So it's simple as it is. All right, I click somewhere else. Now we can go for the convergence check. So this is the checking criteria for stopping the simulation before the maximum iterations are reached. So for speeding up the simulation, so you can tell, okay, my main quantity is the efficiency. So I can choose, for example, efficiency average, and if efficiency average value is doesn't change more than this tolerance over the averaging window, then the simulation can stop before the maximum iterations are reached or the predefined number of iterations are reached. You can choose absolute. So for example, if my tolerance value is 0.1%, then I can keep it in this way. So this is in absolute. Or it can be relative to the current value during the simulation. In the controls, there are parameters connected to the numerical solver and to the numerics in general. So these are the parameters connected to the relaxations, some bounding limits which can stabilize the solution in the early stage of the simulation. So just check it if the range is wide enough to include all relevant physics. And then there are some tolerances of equation solvers and other parameters connected to the solver iteration, but this is the numerical solver, this iterative solver for solving the system of linear equations. Again, scripting can be included in the same way as in the T-mesh. So if you would like to evaluate some specific quantities or any special, it can be scripted via the Python interface. And now the main part, so setting up the boundary conditions. So here, now the question is, what is the goal of the simulation? What are the known parameters? And based on this, you can choose a proper combination of boundary conditions. Typical combination is flow rate and pressure, and the second one could be the pressure and pressure-like boundary conditions. So here, so this is kind of a little bit artificial, small shaped Kaplan turbine. And what only information I found that it can operate something like at 10 meters head approximately. So I can choose the pressure, total pressure, static pressure boundary condition, because I am not aware, I don't know the flow rate at which it operates, but I know the head. So I can set the total pressure at the inlet and static pressure at the outlet, so fixed pressure at the outlet. And for example, I can tell it by the bar units. So I will set bars, and I know the pressure at the outlet, so it can be set like atmospheric pressure at the outlet. It go out from the piping, for example. So I set 1 bar, and at the inlet I can vary the pressures to achieve something around 10 meters ahead. So for example, the middle point could be something like 2 bars to achieve 10 meters ahead. And just to reveal what is happening around this point, I can say higher head for the first point. So typically it's best to start from the higher flow rate, so higher pressure difference, and going to the lower pressure difference. And for example, 0.7 and the lowest. So I don't, if I set pretty low head, so it will not work, I guess. So let's try this minimum pressure difference for the simulation. What we also need to is how to initialize the turbulent quantities. So one of the options is to go for turbulent intensity and hydraulic diameters, because we are in pipe. So I think this is the option number 1. Turbulence intensity, typically we set 5% for internal flows. Hydraulic diameter is the diameter of the piping, which is 16 centimeters here. And reference velocity depends on the flow rate, but I know it because I ran it before, and it's something like 100 up to 200 liters. So if you have this hydraulic diameter, radius is 0.08, squared is 64, and P is something like 3 for the engineers, right? So we have something like 0.02, and if I divide it by the flow rate, we will get something like 10 meters per second, the average speed at the inlet. All right, the next are the walls boundary conditions. We will keep in default here, but the options is if you refine the mesh up to the very fine level, you can go for low Reynolds wall function, or if you would like to mimic some roughness, which can be also used, so you can set the rough walls and set the roughness based on the sand grain roughness, like the granularity of this roughness on the wall, and roughness constant is typically set to 0.5. But in this case, let's stick with the standard slip. So sorry, no slip wall. It means a wall with friction, and this is the default setup for all the walls. So you don't need to care about the other wall parts, but you can set different boundary conditions for the specific part of the wall domain. Then we have interface conditions. So how to treat the information from one side of the component to the neighboring component. The default is AMI, which is a simple interpolation on the interfaces for some application and axial and symmetrical flows. But I think at this elbow side, the flow will be not symmetrical. We can impose the mixing plane, but mixing plane somehow uh, uh, expect or impose symmetrical behavior of the flow. So we will stick with AMI here in this application. And the last but not least is the initial condition. So we have to set some initial guess from which this solver starts. So the pressure at the outlet was 1 bar, so I will set it to 1 bar. Velocity at the inlet, I'm not sure. So for example, I can set this -5 meters per second or -10, which corresponds to my expected flow rate, but it's not so important. It might be some meaningful values, and the turbulent quantities I can initialize by the inlet values. So this is from the simulation point of view, was all the parameters we need to set, and the final is what we would like to see in the report at the end. And we can also set some specific turbomachinery visualization, which are automatically evaluated and put into the report. So here is blade to blade view and meridian average. The setup is pretty simple. You will just set on which part of the domain you would like to see it, what is the hub, what is the shroud, which are important to be set to generate blade to blade views, and in general to create the transformation to the blade to blade view. And the meridian average is pretty similar. Here in the report, you can choose the section which you would like to see: efficiency, torque, head, power, cavitation risk, if defined. So I will keep it as a default. So all are there, and the unit into the report. So for example, volumetric flow rate, I think it's more human readable if it will be in liters in this for this setup. And so you can choose your favorite units to see, and these are some additional operation you can do for some extra specific evaluation and exports, typically to some additional post-processing in different tools, or to be connected to additional tools like external FEA solvers or any other solvers. Okay, so I think I'm too long, so let's save what we have said. So let's save it. Now I will click with the fear on the check button, and let's see. Okay, and perfect, because I have enabled the cavitation risk and I haven't set the custom saturated vapor pressure. So if it's not set, the vapor pressure is automatically evaluated for water at the given temperature. So to be automatically evaluated, the saturated vapor pressure for water, I need to set the reference temperature. So for example, reference temperature will be 10 degrees Celsius. All right, I will click save. I will click check, and for now, I haven't seen, project setup is okay. So keep fingers crossed. And now we can run the simulation. So I can hit run all button. So it will do all the steps which are not yet done. So because the mesh is already generated, it will directly jump to the solver, and now it starts solving our simulation with our boundary conditions and our CFD setup. Just to quickly mention what we can follow. So as Luboš mentioned, we can follow the residuals. We can follow any other quantity which is available. So we can open a new, for example, line chart view. You can go here to the TCFD section. You can enable the quantities section here. And now if you go to the display, you can choose your quantity to follow. So I will go, for example, for efficiency. Then if you click to this view, you can again reset the view on the efficiency. And because sometimes at the beginning of the solver, the values are a little bit wild, so you would like to focus on the more relevant. So you can, for example, you can do it by mouse clicking and dragging the mouse, or you can zoom automatically to all the values and manually, for example, adjust the left axis range. So for example, we can focus on values between 0 or 0% and 80%, and this is what you can see. So the way of following the convergence is looking at the residuals and mainly looking at the goal quantities like efficiency or head or flow rate for this type of simulations. And if the values are calm, not oscillating, and going to the constant value, then this is exactly what we need, what we would like to see for any CFD simulation, that our goal quantities converges quickly and nicely without any oscillations. All right, so this was a quick CFD workflow overview. So as you can see, the first step is to generate a mesh. We always suggest to have a rough mesh, set up a CFD simulation, and then run the simulation, because this will tell you pretty quickly. You don't need to wait for the results several hours. You will get the results pretty quickly. And if something is, okay, sorry, if I go here, and if something is going wrong, you will see it immediately. So sometimes, for example, bad boundary condition combination is set, so the value goes out, or efficiencies. So efficiency is, for example, negative, even the residuals looks good. So it typically means that something is wrong with the boundary conditions or fluid properties, etc. And whenever you will get what you need, so the result will be in the range you expected, or in the range it should be. So then you can go back for the T-mesh part, try to refine the mesh, and you just change a few parameters and you run one click the whole workflow again and go for more accurate results. So this was from my side, from the mesh and CFD simulation setup. And I think here I can end, and for the next webinar we will start at this point to visualize the result, to play with the visualization, etc. Right? So I already heard Luboš.
Yes, yes.
So we can go
Yes,
back
Radek.
to Luboš and
Yeah. Thank you very much. It was really interesting. I followed you carefully. Yes. So let's keep on your screen here, because I would like to ask the audience to ask your questions. It will be a Q&A. So ask your questions. Those brave who stayed with us almost 2 hours. So ask your questions, and we will do our best to answer them. And I think we haven't any questions yet,
okay.
but it's, or do we have some? Yeah, we have a couple of questions. Sorry. We have a few questions. So anyway, Radek, just one question from me which just popped up. When when you when you're happy with your results because everything is being evaluated during the simulation, right? So when you would be happy with the results, would you comment if you can stop the simulation and get the results you have, or skip points?
Oh yeah, definitely. Good question. So about the management, which I didn't mention. So during the simulation, you can manually manage it. So for example, if I see, okay, at the moment the efficiency is converged well, so I can click, for example, skip point, and now it automatically skip the rest iterations and will go for the simulation of the next point. If I would like to see, for example, the instant values, which we show next time, right? You can click to write the results at this point, and then I can display them. And if I want to interrupt or stop the simulation but later continue with the simulation, I can click quit and write. So it will store my immediate results, and later I can continue with the simulation. So this is the quit and write. And if something is wrong and I need to restart or redesign or modificate some parameters, I can abort and discard the setup because I don't need to store them. I will redefine some parameters, and I can run the whole simulation again with the new CFD parameter setup, for example. And
Yes.
last but
Mhm.
not least, for example, you can, during the simulation, you can generate the light report, which will tell you the basic information about the simulation during the simulation. So you can, for example, open the new HTML view, wait for the report, and then the report will appear even during the simulation with the currently simulated data. And the last one, at the end of the simulation, I think I have somewhere here, you will see the full report. So you will see something like this. So HTML view, HTML report with all the relevant and important parameters uh, in the format of the tables and graphs. So you will see the efficiency performance map, the instant values, how it converged, the final values, and it holds for any other quantity which are evaluated. Yeah, including the, for example, cavitation risks, how many cavitating volume or cell were cavitating, cavitation index, and other quantities. But I think this will be a topic of the next webinar.
Yes. Radek, okay, so I'm starting to look at the questions. We haven't many of them. This one is quite important. So, a client is asking whether how you control the mesh layers, the inflation layer in the mesh. If you can, maybe you
Mhm.
did already, but if you can just quickly comment what are the parameters where you switch it on, and what are the basic parameters of the inflation layer and
Okay,
layers in
okay,
the mesh near the wall.
perfect. Mhm. Let's go for it. Maybe I skip this because I'll have a little bit delay with the meshing of the stutter part, with some kind of problem with the STL quality. But about the layers, so the layer can be edited pretty straightforward. So for any wall type patch, you can simply define how many layers you would like to add. So for example, 5 layers, and the parameter of the layer itself is defined in the advanced meshing options section for given component. So any component can have different parameters of the boundary layer. And if I go for the component 2, for which I set, yeah, these 5 layers, I can go for layer mesh parameters, and here you can set expansion ratio, the thickness of the first, final, or whole boundary layer, and other parameters. Relative sizing, if it's relative to the cell size, or if it's absolute. And in this way, you can adjust the boundary layer for any ball patch with its own layer parameters. And then
Yeah.
it's automatically added during the mesh generation.
Yes. Radek, yes, this is good. Thank you for this. Yes, the people typically ask about this. So,
Hmm.
so
Hmm.
there was another question. Uh, a related question to this is someone is asking whether you can change the configuration because not everything from the OpenFOAM and from SnapAX Mesh, not everything is included in the graphical interface of the CAE. And the obvious question is if you can change anything on the disk or in the case manually, and
Hmm.
if it's taken into account later in the simulation.
Okay, okay. So all the changes has to be done via the interface or via the scripting because the program behind the C processor is managing the whole process. But for example, what you can do, you can generate the whole project even with the results, and then you can go on the disk into the project folder, which is for example here where it's yeah, here Kaplan, into the simulation run, into the TCFD, or if you would like to play with the mesh, into the T-mesh, but typically into TCFD, into the stationary solution. And here, this is the OpenFOAM case. You can touch as you want, right? So you can adjust it, but then you need to run it manually for those who are familiar with OpenFOAM.
Uh,
And in this
yes,
way,
yes, yes, yes.
it can be
We
handled.
we it's we would say it's possible, but it's not
Yeah,
recommended.
yeah,
That's
definitely. Mhm.
how I would classify this operation. So it's possible. It's not recommended. And for conceptual changes, we would rather recommend to go via scripting, right? So
Yeah,
you can write down a short script and say what quantity in which dictionary would be changed forever
exactly.
in the workflow if it's not possible in directly in the graphical interface to be saved in the configuration files
Yeah, yes,
normal
yes.
way. So this is how we would proceed with this. And because time is running very quickly, we are already
Mhm.
2 hours
Yeah,
long. The well, yes. Also, a question about the internal point. Yes, this is correct. So someone, it's a more a remark. The project configuration does not it does not save the radius and the origin of the internal point. So yes, that's the paraview property of default property,
Mhm,
and
mhm.
it's not being saved with the project. Yes, so you have to yeah, you change it every time you open the project. So we are sorry for this. And by the way, in the next version, we will have something which helps really a lot. There will be automated internal point function, which will cover 99.9% of cases. So there will be no need of specifying manually the internal point, which is typical bottleneck and annoying little thing. So from the next version, there will be hopefully no internal point needed. Uh, only with a little few exceptions, which is not important. Um, okay, Radek, I'm going to we're going to conclude basically
Yeah,
because we are
perfect,
already
perfect.
very long.
Yes,
So I
yes.
need to, if I find it in this new user
Mhm,
interface,
mhm.
which is sometimes difficult to me because my
Uh-huh.
name is here,
So
Team
I will
CFD
stop
support,
the
I will
sharing
make
my
myself presenter.
screen.
So I'm doing it. Uh, and
Okay,
what
and I
can
think you need to
you,
share the screen, I
I need to
think.
share it again.
Mhm, mhm.
Okay,
Because we
okay,
don't,
okay.
I don't see
I'm
anything
sharing,
now.
so I hope you
Yes,
can see it.
now we
Yes,
can
so
see.
this is again the expert window. Thank you, Radek, for everything. It's been yeah, detailed work. This has been the Q&A session, and this is it. This is really it. So I would like to thank everyone who attended. Feel free to come back anytime. We will gladly answer everything. We are here for you. It's our job, and we like it, and we decided for it years ago, and we still like it. So thank you everyone, and see you sometime somewhere. Thank you,
Yeah.
bye bye.
Thank you. Bye bye. Have a nice day.
Yes, yes.